In the darkness between stars, something hungers, with a gravity so absolute that matter itself surrenders at its boundary and never returns. It pulls without pause. It consumes without mercy. And it has been doing this for millions of years, not in some distant corner of the observable universe, but here, inside the Milky Way, among the same stars that have burned above every civilization humanity has ever built. Separated from Earth by roughly 6,000 light-years, a distance that feels vast by human measure, and yet by the true scale of the cosmos is almost nothing at all. This is Cygnus X-1, the deadliest black hole in the Milky Way. The story of how we found it begins in 1964. Geiger counters mounted aboard a suborbital rocket swept across the sky above New Mexico, searching for X-ray sources beyond the filtering veil of Earth's atmosphere. These instruments represented a technological revolution in astronomy. For centuries, human observation had been constrained to the narrow slice of the electromagnetic spectrum visible to the eye. Visible light, the electromagnetic radiation that Earth's atmosphere permits to reach the ground. But X-rays, produced only in the most violent cosmic processes, are absorbed by the air. They cannot be observed from ground-based observatories. To detect them required lifting instruments above the atmosphere itself, into the black vacuum where Earth's protective shield no longer filtered the cosmos. The rocket-borne detectors opened an entirely new window into the violent universe, a window that revealed objects and processes completely invisible to visible light astronomy. Among the signals they recorded, one blazed with an intensity that no ordinary star could explain. A point of light in the constellation Cygnus, radiating high-energy X-rays with a ferocity that defied every model astronomers had. It was catalogued simply as the first X-ray source identified in the constellation of the Swan, Cygnus X-1. The designation was straightforward nomenclature, a catalogue number assigned to one bright spot among many discovered during those early X-ray surveys of the sky. But this particular catalogue entry would eventually revolutionize our understanding of astrophysics forever. For years, its true nature remained bitterly contested. Some proposed a neutron star, others reached for even more uncomfortable explanations. But as observatories improved and data accumulated, the calculations converged on a conclusion that was, at the time, almost impossible to accept. The mass of the unseen object, derived from the orbital dynamics of a nearby companion star, exceeded the maximum possible mass of any neutron star. It exceeded every known limit. Neutron stars are the collapsed cores of massive stars that have ended their lives in a supernova, but lacked sufficient mass to collapse into black holes. These stars have theoretical maximum masses dependent on the properties of nuclear matter under extreme compression. Different equations of state for neutron star matter produce different mass limits, ranging from approximately 2.0 to 2.3 solar masses, though some exotic models permit slightly higher values. The measurements for Cygnus X-1's unseen companion far exceeded even the most generous upper estimates. The only remaining possibility required invoking an object that had existed purely as a theoretical prediction, a consequence of Einstein's general relativity not yet confirmed to exist in the real cosmos. It crossed a threshold from which there was no return, not even in theory. It was a black hole. At the center of Cygnus X-1 lies a collapsed stellar remnant with a mass approximately 21 times that of our own Sun. Not the supermassive variety lurking at galactic cores, where hundreds of millions or billions of solar masses are compressed into a single region, but a stellar mass black hole, the direct consequence of one massive star's catastrophic death. When that ancestor star finally exhausted the nuclear fuel that had sustained it for millions of years, it could no longer resist the inward pressure of its own gravity. The collapse happened in milliseconds. The outer layers detonated outward in a supernova, and what remained, crushed beyond any density the laws of physics as we know them can describe in ordinary terms, became Cygnus X-1. Its event horizon, the geometric boundary beyond which escape becomes impossible, spans approximately 62 kilometers in diameter, smaller than a city, and yet within that boundary, space-time is curved so severely that no matter, radiation, or even light itself can find a path outward. The event horizon is not a wall or a surface. It is simply the last address in the universe from which the concept of escape retains any physical meaning. But the event horizon alone is not what makes Cygnus X-1 so profoundly dangerous. What makes it deadly is what surrounds it. Cygnus X-1 does not exist in isolation. It orbits in a binary system with one of the most luminous stars in the entire galaxy, a blue supergiant catalogued as HDE 226868, burning at a surface temperature of approximately 30,000 degrees Kelvin, radiating with a luminosity roughly 300,000 times greater than our Sun, while carrying a mass somewhere near 40 times that of our own star. And it is being consumed. The gravitational pull of the black hole, operating across a separation of just over 30 million kilometers, with the two objects completing a full mutual orbit every 5.5 days, is relentless enough to strip material continuously from the outer atmosphere of the supergiant. This stolen gas and plasma does not fall directly inward, as nothing in astrophysics is ever that simple. The mechanics of mass transfer in such binary systems are governed by the Roche limit, the distance at which tidal forces from one body exceed the self-gravity holding another body together. When the expanding supergiant grows beyond a certain threshold during its evolutionary progression, its outer layers extend past this critical boundary. Material becomes gravitationally vulnerable to disruption by the black hole's tidal field. Rather than spiraling straight inward under the black hole's gravity, the stolen material carries rotational motion, forming a structure of extraordinary and sustained violence. An accretion disk. The captured material spirals inward around the black hole, flattening under its own angular momentum into a rotating disk stretching hundreds of thousands of kilometers across. Temperature climbs, not to thousands of degrees, not even to millions, but to tens of millions of degrees Kelvin in the innermost regions, where orbital velocities approach a significant fraction of the speed of light. At those temperatures, the disk does not simply glow. It radiates across the entire electromagnetic spectrum, from radio frequencies through visible light, through ultraviolet, and deep into X-ray energies that would destroy biological tissue on contact. Cygnus X-1 emits X-ray luminosity exceeding the total energy output of our Sun by a factor of more than 25,000. Every second, continuously. It has maintained this output for millions of years, and the companion star feeding it still has mass left to give. From 6,000 light-years away, it remains among the brightest X-ray sources in the entire sky. Above the disk, suspended in the magnetic fields threading its innermost regions, exists a structure physicists call the corona, a halo of extraordinarily hot, diffuse plasma where temperatures climb into the billions of degrees Kelvin. At these energies, particles race at velocities approaching that of light, scattering X-ray photons upward and outward in patterns that carry imprinted signatures of the gravitational geometry surrounding the event horizon. When astronomers examine the spectral fingerprints encoded in this radiation, they are reading information about a curvature of space-time, studying the physics of gravity at its absolute extreme, at the last boundary before the mathematics of general relativity confronts its own limits. The black hole also spins. Measurements of the innermost accretion disk indicate that Cygnus X-1 rotates at a rate very close to the theoretical maximum permitted by general relativity. This is not a trivial detail. A rotating black hole warps space-time differently than a stationary one, dragging the fabric of space itself around with it in what physicists call frame dragging, creating a region outside the event horizon known as the ergosphere, where space-time is pulled along with the black hole's rotation faster than light could travel in the opposing direction. Everything is swept along. Even light cannot hold its ground. When instabilities in the accretion disk trigger outbursts, columns of relativistic plasma blast outward from the polar regions of the system, extending for light years, heating and compressing the interstellar gas they traverse, reshaping the local environment of space across distances that dwarf any human scale of reference. The precise mechanism driving these jets remains one of the deepest unsolved problems in astrophysics. What is understood is that the combination of an actively feeding black hole, a rapidly rotating ergosphere, and powerful magnetic fields threading through an intensely hot accretion disk can produce outflows of energy and matter that alter the structure of interstellar space for vast distances beyond the system itself. However, the companion star HDE 226868 cannot endure indefinitely. Blue supergiants burn through their nuclear reserves at catastrophic rates. A star of its mass carries a total lifespan measured in only a few million years, a blink of an eye by the standards of stellar evolution. Already, it is almost certainly in the advanced stages of its nuclear burning sequence, progressively fusing heavier elements in its core as hydrogen exhaustion drives it toward its own violent conclusion. The evolutionary timescale of massive blue supergiants differs dramatically from that of stable stars like our Sun. Our star, a middle-aged yellow dwarf, has burned steadily for approximately 4.6 billion years and possesses sufficient hydrogen to continue for another 5 billion years. But this star, with 40 times our Sun's mass, burns through its nuclear fuel with profligate intensity. When it finally collapses, the resulting event could produce a second neutron star, a second black hole, or an explosion energetic enough to entirely disrupt the gravitational bond between the two objects, sending them off on separate trajectories through the galaxy, or they may remain bound. If both objects survive as black holes and remain gravitationally linked, they will begin the long, slow in-spiral that general relativity demands of any pair of massive, compact objects orbiting in each other's presence. Across astronomical timescales, the emission of gravitational waves carries energy away from the system, shrinking the orbit imperceptibly but continuously, until the two objects finally merge in an event of violence so concentrated that the energy released in fractions of a second exceeds the total light output of our Sun across its entire 10 billion year lifetime. The collision would send gravitational waves propagating outward through the fabric of space-time at the speed of light. That future lies millions of years distant, perhaps far longer. But the physics that will produce it is already in motion. For now, Cygnus X-1 simply continues as one of the deadliest objects in the galaxy.